Let us continue thermodynamic terms, reversible and irreversible process, path function. Okay, path function means it depends on path of the process. That means whether it is reversible or irreversible. Okay, for which we will take another example. We will take now isothermal free expansion of ideal gas. Free expansion of ideal gas, that we will take. Isothermal free expansion of ideal gas, that point we have taken. Sorry. Now, here given is a free expansion is a given word. So free expansion means what we have to do, that we'll see. Now we will take ideal gas. Ideal gas we have to take. Here we will keep piston, we will keep. We placed a piston. Next, this ideal gas is having some pressure. For example, to atmosphere, it is having some temperature. For example, 27 degrees Celsius. It is having certain moles, some x moles, and it is having some volume V1 liter. Okay, it is undergoing free expansion. That means it is undergoing expansion. But this expansion, how it should be there? It should be free. How it should go for expansion? Free. Free in the sense there is no obstacles. There is no opposing force. There is no opposing force in the sense external pressure should be how much? How the external pressure should be there, and how the weight of the piston should be there, and how the friction between the piston and vessel should be there. Okay, now this ideal gas is going for expansion. How the expansion should be there? Free in the sense when it is going for expansion, nothing should disturb this. Nothing should disturb this in the sense how the external should be there. The external should be vacuum. Piston weight should be weightless. Friction should be frictionless. Then only free expansion is possible. Okay. Now it is going for what in the sense free expansion. We can say what is the work done by the ideal gas in this process. What is the work done by the ideal gas in this free expansion process? Okay. Now work done in the sense piston is weightless. Therefore, against piston, no work is done by ideal gas. Between piston and this vessel, friction is frictionless. So against friction, the ideal gas is not doing any work. And external is vacuum. Therefore, ideal gas is not doing any work against external. Therefore, it is not doing any work against anything. Therefore, what is the work done? Work done is 0. Therefore, isothermal free expansion of ideal gas, in this case, what is the work done? That work done we can say as 0, we can say. Set. So isothermal free expansion of ideal gas means work done is equal to how much in the sense work done is 0, we said. Okay. Next we will see compression we will take. Now we'll take a compression, we'll take in that how the work done will be there, that we'll see. Now we are taking isothermal irreversible compression of ideal gas. Okay, sir. Now we are taking compression, we are taking, sir. Now we are taking a vessel. In this vessel we will take a ideal gas. We are taking ideal gas. Its pressure is how much in the sense 1 atmosphere. Number of moles is x moles. Temperature is 27 degrees Celsius, and the volume is V1 liter. Volume is V1 liter. Pressure is P1. Pressure is P1. Volume is V1. Okay. Now we will give the external pressure. How the external pressure should be there when compared to pressure of the gas, such that gas can undergo compression? Sir, external pressure should be greater than this pressure of ideal gas. Then only ideal gas will undergo compression. Okay. So external pressure we will keep it as 2 atmosphere. Sir, external pressure 2 atmosphere in the sense this ideal gas is undergoing compression. So piston comes down. Okay. So here ideal gas, Here pressure becomes 2 atmosphere. This is the final pressure. Number of moles no change because closed. Temperature is constant because isothermal process. Volume is reduced. Volume is reduced now. This volume is smaller than this volume. This pressure is greater than this pressure. Okay. Now what is the work done? So work done is equal to minus external pressure into change in volume. Okay. For expansion, this is the formula. For compression also, this is the formula. Okay. Here minus sign will be there for both. For expansion as well as compression, here minus sign will be there. Okay. So, but delta V, if you see that expansion means delta V is positive, compression means delta V will be negative. Okay. So, now we will see graphically this work done. We will see graphically we are seeing the work done. Okay. Now we will take pressure in this axis, volume in this axis. Now it is coming under which category in the sense Boyle's law. Why? Because here in this case, what is changing in the sense pressure increases, number of moles remains same, number of moles remains same, temperature remains same because isothermal process. Volume what happens means volume decreases. So pressure increases, volume decreases. So pressure is inversely proportional to volume. Therefore, it obeys Boyle's law. Boyle's law in the sense rectangular hyperbola. Rectangular hyperbola. Okay. Now we will give initial. This is suppose now initial and final condition we have to give. Okay. 2 points we have taken. Which is initial? Do you say? Okay. Which is initial in the sense this point is initial. This point is initial. V1 is less. V1 is high. Then this point will be final. This point will be final. It is P2 V2. Okay. Now work done is equal to what in the sense minus external pressure. External pressure is equal to final pressure. Final pressure in the sense P2 set. Final pressure in the sense P2 that we have taken. Next delta V. Delta V is called change in volume. Change in volume means this final volume minus initial volume. Final volume is how much means this much. It is final volume. Initial volume is how much means this much. Therefore, this is the external pressure. This is the pressure. This is the external pressure. This is the external pressure. This gap is called change in volume. This gap is called change in volume. This is external pressure. Therefore, what is the work done in the sense this is the work done. Okay, this is the work done. This area is called work done. We can say this area is called work done. Okay, so it is work done in the work done for this compression. Okay, so for this compression, what is the work done we have discussed. Okay, so isothermal irreversible, it is irreversible process, irreversible compression. It is single step process. In this single step process we got work done. Now we will see this same thing in two steps. We will see same thing we will see in two steps. How the work done will be there, that we will see. Okay, so now we have to go for two steps process. Two steps process will go. Sir, first we will take, now here what we are taking in the sense ideal gas we will take. So we are taking ideal gas. What is the pressure of this one? The pressure P1 is equal to how much in the sense 1 atmosphere, and number of moles is x moles. Temperature is how much? 27 degrees Celsius. Volume is how much? V1 liter. Okay. So what we have taken here? What we have taken here? Same thing we have taken. What is the initial stage here? The same initial stage we have taken. Okay. Then how the external pressure should be there? How the external pressure we have to give in the sense give 1.5 atmosphere, but don't give this 2 atmosphere. Don't give this 2 atmosphere. Okay, 2 atmosphere if we give, we will get final stage. We should not get final stage. We have to go final stage by 2 steps. Therefore, we are giving external pressure how much in the sense not 2, less than 2 we have given. Set. So final external pressure we have given 1.5 atmosphere. External pressure is greater than this pressure of this gas. Therefore, what happens means compression takes place. Okay. So compression takes place here we said. Okay. So here what is happening means compression. Okay. Now compression. Now what is the pressure? The pressure is 1.5 atmosphere. Now we can say volume is this much. We can say volume is this many liters. Number of moles, temperature remains same. Okay. Next, again we will change the external pressure. Now we will give the external pressure how much in the sense 2 atmosphere we will give. Okay. So we have given external pressure here 2 atmosphere. No, that 2 atmosphere we have given. Okay, 2 atmosphere we have given. Now we will see the work done. We'll see. Okay, now here compression takes place. Now what is the pressure? Means the pressure is 2 atmosphere, volume is V2 liter. Okay, so here final stage and here final stage remains same. Here initial stage and here initial stage remains same. Then what is the difference? It is a two steps process. That is what in the sense a single step process. Okay. Now here work done is there. Here also work done is there. Total work done in the sense sum of these two. Sum of these two is called the total work done. Set. What is the total work done? That we will see graphically. We'll see that total work done. We'll see. Okay. Here we will take pressure. We'll take. Here we will take volume. Then we are getting graph rectangular hyperbola. We are getting. Now we will see what is the initial state. It is the initial state. Okay. P1 V1. It is initial state. Final state is this, that is P2 V2. This is final state. This is a intermediate state, that is PI VI, intermediate state. Okay, intermediate state. Now first step work done. First step work done W1, that we want external pressure. External pressure means this PI. Okay, external pressure means this PI. It is the external pressure. Now what is the change in volume? Intermediate volume, that intermediate volume is this much. And V1 initial volume, that initial volume is this much. And external pressure is this much. External pressure this much. Therefore work done in this step, work done is this much. Work done is this much. In the second step, what is the work done? In the second step, external pressure is 2 atmosphere. 2 atmosphere is the external pressure. Okay, external pressure is 2 atmosphere. For this change in volume is this final volume V2 minus this intermediate volume. Okay, this final volume we will take this much. This is the final volume, and the intermediate volume is how much in the sense this much. This much is the intermediate one. Therefore, what is the work done here? What is the work done in the second step in the sense second step work done is this much. Okay, so second step work done is this much. First step work done is this much. Total work done is this much. Okay, now you see the total work done in the two steps process. Here two steps process. Here you see the total work done, and you see the single step process. You see the total work done. Okay, so in single step process means how the work done is there. You see in the two steps means how the work done is there. You see. Okay, now we will see multi steps. Multi steps means how the work done will be there. That we will see. Now here pressure we have taken. Here we will take volume. Now we will draw the graph. The graph is a rectangular hyperbola like this. We are getting set. So now we will say the points. It is the initial point. It is the initial point. It is first stage. It is the second stage. It is the third stage. It is the fourth stage, fifth stage. Like this, it continues. Final is it is continuing like this. Okay. Now, in the first stage, what is the work done? That we will see. First stage, it is the first stage work done in the sense this neighboring pressure we have to take. Okay, neighboring pressure. Then this volume and this volume, it is called work done. So, in the second stage, what is the work done in the sense next step external pressure we have to take. Okay, that change in volume we have to take. It is a second step work done. Then third step work done we'll see. It is a third step work done we can say. Third step work done. Next we'll see fourth step work done. It is fourth step work done. Next we are taking a fifth step work done. It is fifth step work done. Okay. Next we will take a sixth step work done. Next it is sixth step work done. Next we will take it is seventh step work done. It will go like this. It is the total work done in the multi steps. Okay. So that it is what in the sense irreversible process. In this irreversible process, how the work done is there. You see, if number of steps increases, if a number of steps increases, what happens to the work done? Work done on the gas, work done on the system, work done on the ideal gas. How it is there? That is decreasing. Okay. If number of steps increases, work done on the system, what happens means it decreases for this irreversible process. Now we will take reversible process. We will take. Okay. So now we are taking a isothermal, reversible, isothermal, reversible, compression of ideal gas. of ideal gas that we will take. So now initial state we will take. Initial is what in the sense we are taking ideal gas we are taking. Then what is the pressure in the sense 1 atmosphere will take, a number of moles x moles will take, temperature 27 degrees Celsius will take, and volume is V1 liter. Okay, now we have to give external pressure. How the external pressure should be there means that should be greater than the pressure of the system, then only compression is possible. Therefore, how much we will take in the sense that we will take this much. This much is the pressure. Now, pressure difference between these two is infinitesimally small. Okay, like this only should be there. Like this, how many steps we have to take in the sense infinity steps you take. At each step, you leave the system for infinity time such that system and surrounding get equilibrium. Okay, you have to do like this. Then, what is the work done? Work done for this in the sense minus 2.303 NRT NRT log V2 by V1. It is the formula for this process. For expansion, what is the formula you got? Same formula for this also. Okay, this negative sign you keep for expansion as well as compression, both. But V2, V1 will change. Okay, V2 will be greater than V1 for expansion. V2 will be smaller than V1 for compression. Like this will be there. Now, what is graphically what is the work done? We'll see. The pressure is here, volume is here. It is rectangular hyperbola will take. Now it is initial state will take, it is final state will take, then area under this curve, area under this curve is called a work done. Now work done in irreversible process, irreversible process work done we have seen, irreversible process work done we have seen. Now reversible process work done also we have seen. Okay, reversible process, reversible process work done also we have seen. How the work done is there? Now reversible process in the sense area under this curve is called a work done here. Now irreversible process in the sense see the work done, that means some area occupied, some, that means above the curve also some area occupied in the work. Here also see above the curve also some area occupied by the work. Now here you see in the single step means above the curve also where some area is occupied by work. Therefore irreversible and reversible. How the work is there means irreversible process in the sense work done is high, reversible process in the sense work done is low for compression. But for expansion it is reverse. It is reverse. Okay, now you say that now reversible process, reversible path work done you see, irreversible path work done you see different. Therefore irreversible path, reversible path work done is different. Therefore this work done, that means work done in isothermal compression of ideal gas comes under path function, we can say. Work done in isothermal compression of ideal gas comes under path function, we can say. Even expansion also comes under a path function only. Sir, now we will see this one. Now isothermal free compression, isothermal free compression of ideal gas, is it possible or not, you say? Isothermal free compression of ideal gas, is it possible? Free expansion we said, free expansion means vacuum we said. Here free compression means is it possible? Free compression in the sense if compression in the sense what, external should have higher ability to do work than system. Then only compression is possible, we can say. External should have higher pressure when compared to pressure of the system, then only compression is possible. Here free compression in the sense free in the sense what, external should not be there, then only free. No, if external is not there, how compression is possible? Therefore free compression is not possible. Okay, but free expansion is possible, free expansion is possible, whereas free compression is not possible, we can say. Sir, next we'll see about state functions. We'll see, now we have seen path functions, we have seen. Now we will see about state functions. Okay, so what is state functions, that we'll see. What is a state functions? State functions in the sense it is depending on initial and final states of the system but not path of the system. State functions means these functions depend on initial stage and final stage but not depend on path. So it is depending on initial and final, that's what they said. Okay, now we will see. Here it is single step process. Here initial pressure is P1. Okay, it is irreversible process. Here initial pressure is P1, 1 atmosphere. Now we will see it is reversible process. Initial pressure is P1, 1 atmosphere. Okay, so in this reversible process, initial volume is V1 liter. In this irreversible process, initial volume is V1 liter. So here in the irreversible process, final pressure, reversible process, final pressure remains same. But what is the work done? Irreversible means work done is high. Reversible means work done is low. Therefore, in the state functions, shall we say pressure, temperature, volume, number of moles are state functions, whereas work done, isothermal work done is not state function, because isothermal work done for irreversible process and reversible process different. So isothermal work done depends on the path of the process. Therefore, isothermal work done is not a state function, whereas pressure, temperature, volume, these are the state function. Okay, so another terms also there, that is internal energy, enthalpy, entropy, Gibbs energy, these and all are there. They are coming under which one in the sense state function, but what they are, that we were to discuss later. Set. Okay, now we will go for a first law of thermodynamics. We are going for first law of thermodynamics. First law of thermodynamics we will take. First law of thermodynamics. What first law of thermodynamics says? First law of thermodynamics says that energy can be transferred from one form of energy can be transformed into another form. One form of energy can be transferred into another form. Suppose we are taking petrol. It is a form of energy. That petrol we are using in the vehicles, in the sense it is converting into mechanical energy. Therefore, vehicle is moving. And some energy is converted into heat. Therefore, exhaust contains hot gases. Exhaust contains hot gases, isn't it? So one form of energy is converted into another form of energy. We are taking food. Food is a form of energy. We are taking that food in the sense that is converted into required energy for the body. For the body in the sense for body growth, for body work, all this we are doing work. For that work we are getting energy from food. So food is converted into energy in the form of what? Work energy, and all the growing parts in the body, for everything. That means we can say one form of energy can be converted into another form of energy. This is the real fact. Okay, set. So first law of thermodynamics says what, in the sense one form of energy can be converted into another form of energy, it says. But it says that we cannot create energy. Similarly, we cannot destroy energy. Okay, suppose we are destroying energy in the sense that means what? That is destroying means that is converting into another form. Okay, so we are creating in the sense what? We are converting some other form into this form. That is called creating. Okay, only creation, only destroying, that is not possible. That's what first law of thermodynamics says. Okay, then this says that isolated system, in the isolated system, energy of the system is a constant. In isolated system, energy of system is a constant, it says. Why? Because a isolated system means what? It is completely detached from the surrounding. Between the system and surrounding, there is no contact at all. Then between the system and surrounding, there is no energy exchange. There is no matter exchange. Therefore, a isolated system means energy remains constant. So, energy of isolated system constant, we can say. Then it says about some machine. What is that called? Means perpetual motion machine. Perpetual motion machine. Okay, it says about this. Okay, what is meant by perpetual motion machine? Means we should not supply any energy. We should not supply any energy, but it has to work. But it has to work. That is called perpetual motion machine. It is not required. It is not in need of any energy, but it will work. Without considering, without having any energy, without taking any energy from surrounding, it will work. That is called perpetual motion machine. First law of thermodynamics says that we can't construct such a type of machine at all. Constructing such a type of machine is impossible. Perpetual motion machine means it will not take any energy from surrounding, but it will work continuously. That is called perpetual motion machine. This machine we cannot create at all. We cannot create this like this machine is impossible to construct. It is not possible, sir. Okay. Then first law of thermodynamics says some other points. What is that? Some other points we'll see. Now that means a mathematical form of first law of thermodynamics we'll see. Mathematical form of first law of thermodynamics. Now we will take here some ideal gas we'll take. Here some ideal gas we'll take. This having suppose it is having suppose pressure P1, volume is V1, temperature is T1, number of moles is N1. Like this is. Now you say that in this ideal gas molecules, these ideal gas molecules can move from one place to another place or not? Yes. It is moving from one place to another place continuously in the sense it is having kinetic energy or not? Yes, it is having kinetic energy. That energy is possessed by this gas. Therefore, that energy is called internal energy of this gas. Internal energy we can say that energy is called internal energy. Otherwise we can say intrinsic energy. Intrinsic energy we can say. Okay, this ideal gas molecules move from one place to another place continuously. That means these gas molecules are having kinetic energy. That kinetic energy is nothing but internal energy of this gas. Okay, that internal energy is how much in the sense u. Okay, internal energy of this ideal gas is u1. So now, to this ideal gas, let us pass, let us give this much amount of heat. This much amount of heat, let us give. If we give this much amount of heat, what happens to the kinetic energy of gas molecules? Rising, increases. Kinetic energy increases in the sense, what happens to the internal energy? Internal energy also increases. So, next, next we will keep a piston over into this piston we will keep and we will go on keep some weights. We will go on keep some weights. What will happen? Piston will go on come down. No, piston is going on coming down in the sense external does work. External does work on a external does work on a gas work on system. So external is doing some work on the system in the sense this system is gaining some energy. Gaining some energy in the sense this system kinetic energy. This system energy is changing. This system internal energy rises. Therefore, now the internal energy of the system is how much in the sense U2 will take. Here work done is equal to some W will say. Okay. Now, what is the change in internal energy? That we'll see. Now, we'll take a change in internal energy. Change in internal energy equal to final internal energy minus initial internal energy, that is equal to delta U. That delta U is equal to this heat plus this work. Okay, therefore first law of thermodynamics says that delta U is equal to Q plus W. It is the mathematical form of first law of thermodynamics. Delta U is called a change in internal energy. Q is called a amount of heat involved. W is called a work done. So here Q is called amount of heat involved means it is supplied or what. That means in whatever the form we can take, whether it is exothermic or endothermic, in whatever the form you take, as per that sign will change. That's all. This W in the sense work done on the system or by the system means anything we can take. Okay, the work done on the system we can take, otherwise work done by the system we can take, anything we can take. Work done on the system means system will gain work. Work done by the system means system is doing work by losing energy. That's all, isn't it? Work done on the system means system is gaining energy. Work done by the system means system is losing energy. Okay, that's what this work says. This Q is equal to, if system is absorbing heat, it is gaining energy. If it is losing heat, it is losing energy. That is what this Q says. So delta U is equal to Q plus W. We can say it is a mathematical form of first law of thermodynamics. Now conclusion of first law of thermodynamics we will say One point is energy can be transferred from one form into another form. Okay. Next, energy cannot be created. Next, energy cannot be destroyed. Okay. Next, energy of isolated system remains constant. Next, perpetual motion machine we cannot construct. Perpetual motion machine we cannot construct. Then mathematical form of first law of thermodynamics. Mathematical form of first law of thermodynamics means delta U is equal to Q plus W. Okay, sir. This is about what in the sense first law of thermodynamics we can say. Next we will see about internal energy. We'll see. Now we'll go for internal energy. Now we are taking internal energy. For internal energy, symbolic representation U will take, sometimes capital E also will be given. Sir, okay. So what is internal energy? Internal energy means what? Energy possessed internally, isn't it? Energy possessed internally. If we take a human being also, if we take a human being is doing work, is doing work. Why? Because human being is having energy, energy possessed by the body is having energy, therefore we are able to do work, isn't it? Sir, okay. So that means each and every matter possess energy. Okay, whatever the matter you take, whether it is gas or solid or liquid, whatever the matter you take, that is having energy. So all the matter possess energy. That energy is called internal energy, we can say. So internal energy that U is in the form of what? In the form of what means no doubt in the form of kinetic energy. Kinetic energy in the sense rotational, vibrational, translational, like this forms. Next one is what means potential energy. Potential energy means interaction. Interaction is nothing but attraction and repulsion. Now we can say between any two bodies attraction is possible. Whatever the bodies you take, whether living thing, non-living thing, whatever you take, between any two bodies certainly attraction will be there, but magnitude varies from one body to another body. Okay, this interaction, attraction and repulsion is called a potential energy. Sum of these two is called a internal energy. So internal energy of any matter you can take, whether it is gas or solid or liquid, any matter you take, how the internal energy will be there means internal energy equal to sum of kinetic energy and potential energy will be there. So so what is internal energy? We said next. Internal energy is coming under which function in the sense state function. State function in the sense what? It should depend on initial and final states, but not depend on path of the system, path of the process. Okay, it is state function. Then it is a extensive property. How do we say it is extensive property? Means suppose you take one banana, how much energy we will get? You see, if you take two banana, how much energy we will take? You see that if number of bananas more energy we are getting, isn't it? That means if number of bananas more, then total energy content will be more. Therefore internal energy depends on what? Extent the depends on quantity, therefore it is extensive property, we can say. So therefore internal energy is extensive property. It is a state function, it is not path function, it is not depending on path of the system, it depends on state of the system. It depends on state of the system, therefore it is a state function, we can say. Sorry. Next we'll take a first law of thermodynamics. We'll take delta U is equal to Q plus W. Will take, now this Q will take, this W will substitute minus P, delta V will substitute, therefore delta U is equal to like this. Okay, delta U is equal to like this we have taken. Now we will take the condition what in the sense change in volume is zero. That means volume remains constant. That condition will take, volume remains constant. That is the assumption we are taking, that is the condition we are taking. When volume of the system remains constant, delta V is equal to 0, then this term vanishes. Then we can say delta U is equal to Q at constant volume at a given temperature. Okay, so delta U is equal to what? Q at constant volume at a given temperature. So how do we define delta U? How do we define change in internal energy? Change in internal energy is equal to amount of heat involved in a process at constant volume and at a given temperature. Okay, so amount of heat involved in the sense involved means what? Whether absorption, otherwise liberation. whether absorption, otherwise liberation. System can absorb heat energy, otherwise system can liberate heat energy. That depends on the process, whether it is exothermic or endothermic, depends on that. Okay, so delta U is equal to, so remember that delta U is equal to what, in the sense Q at constant volume and a constant temperature, like this we can say. Next next point we will take a, now we will take a closed vessel. We will take, in this closed vessel, what we will take, in the sense 1 mole of gas we will take, 1 mole of ideal gas we are taking. This is at what temperature, in the sense 27 degrees Celsius. Okay, now since it is closed, number of moles will remain same, number of moles will remain same, and volume remains same because it is closed vessel. Now what shall we do, in the sense let us supply heat, let us pass heat into this. So if you pass heat into this, what happens, temperature rises. Let us make the temperature to become like this, let us make the temperature to become like this. That means 1 degree rise, otherwise 1 degree reduce, anything you can take. Okay, now volume you kept constant and number of moles kept constant because it is closed vessel. Now you have supplied heat energy, what happened means temperature raised. Okay, now here gas molecules are having kinetic energy and potential energy. Sum of kinetic and potential energy is called a internal energy. Here gas molecules are having kinetic energy and potential energy, that sum is equal to internal energy, that is U2. Here temperature is high, therefore here internal energy is greater than this internal energy, we can say. Now change in internal energy, delta U is equal to U2 minus U1, that is equal to amount of heat supplied, isn't it or not? Because how much heat supplied, corresponding to that temperature is raised, isn't it? How much heat you have supplied, that corresponding to that temperature is raised. This heat involved, this heat involved is called CVM. CVM is called what, in the sense molar heat capacity, molar heat capacity at constant volume. Molar heat capacity at constant volume, we can say. Molar heat capacity at constant volume, we can say. Have you got an idea? Okay, so what is CVM? You got an idea? CVM means molar heat capacity at constant volume, we can say. Okay, now let us consider that number of moles. Let us multiply let us take a number of moles, 2 moles. If you take, you are taking 2 moles, that means we are raising temperature correctly 1 degree Celsius only we are raising. We are raising temperature 1 degree Celsius, means how much heat you have to supply into 2q we have to supply. Now we will say change in internal energy is equal to 2q, which is equal to 2 into CVM. 2 into CVM. CVM means what? Molar heat capacity at constant volume. That means for 1 mole, for 1 mole. CVM, how to define CVM? To define CVM, you have to take 1 mole of gas and you have to raise the temperature 1 degree, otherwise you have to reduce the temperature 1 degree. For doing that, what amount of heat involved, that is called molar heat capacity at constant volume. Now we have taken 2 moles, we have taken, for 2 moles we have taken, but 1 degree we are raising. Now what is the amount of heat involved, in the sense 2q? 2q is equal to delta U, but it is equal to 2 CVM, 2 times CVM. Set. Suppose if we take number of moles n, we are taking number of moles, how much, in the sense n moles, then 1 degree only you are rising, then how much heat we have to supply? That means n into q. Therefore now we can say delta U is equal to nq, we can say, but it is equal to n into CVM, we can say, n into CVM, because n moles we have taken. Therefore, and if you raise the temperature, suppose if you raise the temperature 2 degree you are rising, 2 degree you are rising means like this, 29 degrees Celsius, 2 degree you are rising. If you rise 2 degree, what will happen? Into 2 we have to take, into 2 heat we have to supply. Therefore delta U is equal